So we're going to represent our machine learning model mathematically. But a machine learning model is essentially a function. Basically, we have y hat, which is usually the predicted value, as a function of x, which are normal input features. Input features, for example, if we are looking at predicting whether something is a cat or dog, the input features could be the ears, the length of the ears, the length of the nose, probably the weight of the animal. Those are input features. And then psi theta will be the model parameters. These are the parameters that are learned from the data that is provided. For example, in our simple model, we can have different weights assigned to each feature. So we have the predicted model is a function of the input features provided in the model and the learned parameters. The learned parameters, which could be weights and biases. For example, you can have y is equal to w1x1 plus w2x2 plus wx3 plus beta, where w1 represents the weights assigned to each feature. So we will get this little bit of understanding of what a model looks like. From here we can give an example here. We have said here our y hat is a function of x and theta, is a function of the input feature and the weights and biases, whereby y hat, the model is just what's going to be predicted. The x features could be the size of a house or number of bedrooms. For example, if you are predicting the price of a house, the input features could be the size of the house or the number of bedrooms in the house or how many square feet each room is. Then theta are the weights and biases, just the function or rule that combines all these together, the weights and parameters, and to give us a simple model. In plain terms, the prediction is the model's formula with inputs and learned settings or parameters. For example, predicting car price, whereby x is the mileage, we try and predict the price of a given car. We may look at data, we have data available for the distance, that's the mileage, the brand of the car, the age of the car, the type of engine of the car, and the size of engine size. So, basing on this, we obtain weights, and then we get the predicted price. Graphically, you can see it here. The function, if you get the input features, parameters, it'll give you the price, the predicted value, the y hat. So in simple terms, input features can be anything that the values that we can get from the data. For example, we can have some are numeric. For example, we can have the age or the temperature. Some can be categorical, for example, color or country, or some can be derived. For example, average monthly spending can be determined from finding how much they spend over 6 weeks, and then you find the average. Then the quality and relevance of features heavily influence model performance. So we'll look into that. Can come directly from raw data or engineered from multiple sources. Yeah, basically this is what they call feature engineering. You can find, probably you want to consider in your model, if you have a model and you have the size of room size, basically if you want to get like the area of the place, you can get the room size squared. That's a little bit of engineering, We'll look into that, how to feature engineer. So more examples of features, input features. For example, in this case, we're looking at an example of house price prediction. We're looking at the square footage of the house, which is a numerical variable, the number of bedrooms, which is numeric, and the location, which is categorical. The location of the houses may vary. Some may be in probably in California, another one is in Texas, So location will have to handle numeric data and categorical data in our model as we go forward. We'll be aware of that difference on the type of features. So if we look at an example of determining spam, whether an email is spam in your mailbox, when you get sometimes mail in your inbox, sometimes the algorithm will separate the junk, the spam, from the actual good mail. But how does it do that? It will look at a number of things. To look at if your email comes through and has certain links, it will look at that. It will consider that. It will look at the presence of certain keywords like win or free. Sometimes you find that spam or these scams that come in the mail, in the emails, have things like win $1 million, win a lottery quickly. So it looks at such keywords as input features, and some of these are binary. We have it will look at the sender domain, things like that. So when it considers all these things, it is able to classify whether an email is a spam or it's a good email. Another example is the customer churn prediction. Okay, if we could look at the number of months as a customer, the average monthly spent. If we look at customer calls in the last 3 months, we're able to determine the customer churn prediction. So in summary, a simple example, let's use other examples where we actually represent the weights of W1, W2, up to Wn, and B as the bias. Our model would look as Y hat, which is the predicted value, is going to be a function of weight 1 and input feature 1. This weight 1 corresponds to X1. Our algorithm will determine the value of W1, which it will learn from the data. W2 is the weight 2, which is corresponding to the second input feature, up to Xn and Wn, plus determine the bias, and that will be our simple model, simple representation of our prediction model. In this instance, this is our X here. Our X1 will have been number of months. These are the input features. These ones, as we see them, for different algorithms, we will determine different input features and different weights. So a few key things to learn about parameters. Parameters are learned automatically during training. You don't set them manually. What do I mean? These W1s or W2, Wn, once we feed in the data, it will figure out what value they take on. And once they're learned, they remain fixed during prediction. They are different from hyperparameters, which are set before training and control how the model learns. So hyperparameters, we shall get to look at hyperparameters when we go later on in detail. We may look at things like the learning rate. We can determine the learning rate. Normally, we want to have a learning rate that is small, not too quick, the speed at which the model is going to learn. So we will get to that later on as we build our models. Those are what they call hyperparameters. But in these instances, we're looking at the parameters as the weights and biases. Things like hyperparameters, we shall get to them. Usually smaller parameters are good so that our model learns slowly. Learning rates, you may find learning rates having a value like 0.01 or 0.02, determining the rate at which our model learns. If it learns slower, it performs better. So these learning rates are different from, these parameters are different from hyperparameters, So examples of parameters, So in a regression model, we have W, the weights, W's, the bias intercept, B, which are learned from the data. And so we shall now go to training a model. We shall